Masers are common in our own galaxy, but they can also be detected in external galaxies. When we see these kinds of masers, they have to be intrinsically much brighter than the kind we see in our own galaxy in order for us to detect them. We call those megamasers. The term mega there is referring to the fact that they're 1,000,000 times more luminous than the kinds of masers we see in our own galaxy. Some megamasers come from the gas that's very close to the black hole in what we call an active galaxy. So the active galaxy is a galaxy that has a supermassive black hole in the center and a disk of gas that is falling into the black hole and creating lots of energy. In these disks, the masers are actually beamed out in the plane of the disk. So if we happen to be seeing a galaxy where the disk is almost perfectly edge-on, then the megamasers in that galaxy will be bright, and we can detect those. There can be other galaxies that have a disk that's face-on, as we see it, and in that case, the masers, they're still there, but they're beaming into a different direction, and so from our vantage point, we wouldn't see very bright maser emission in that particular galaxy. What we like to do is try to find these cases where we can detect a megamaser. The way we do that is, first of all, we limit our searches to these galaxies with the edge-on structure. We call those Seyfert-2 galaxies. Beyond that, the searches are very sensitive to just what the tilt in that orientation is. We need it to be perfect, and so the detection rate is still quite small. We've looked at thousands of galaxies in order to detect only about 30 galaxies that we know have these disk megamasers. That's not very many. But the good news is that when we do detect them, we can do some really cool things with them. First of all, we can measure the mass of the black hole in the center of the galaxy better than any other method. So apart from the black hole in the Milky Way galaxy, the megamaser method gives us gold standard black hole masses. It's the best way to measure those. Another thing we can do is we can actually see what the formation of that accretion disk looks like in these galaxies. So we can see how it's oriented on the sky. Sometimes we can see that they have some warp to them, and we can measure what the properties of that warp are. But the principal goal, actually, of the Megamaser Cosmology Project, you can see the word cosmology is in there. And so the principal goal is we try to use these disks to measure the distances to the galaxies. And it's a really elegant method. What we do is we use the maser emission to understand the dynamics, and we can get the linear size of the disk. In other words, we can measure how big that disk is in light years. So a disk might be about a light year in size. Then we can make a map of the disk, and we can see how big it is in angular size. In other words, how many milliarcseconds is that disk. And then it's just a matter of triangulation. We know a linear size and we know an angular size, so we can measure the distance to the galaxy. It turns out measuring distances to galaxies is really difficult. And so because we can do it with this relatively simple geometric method, it gives us a valuable insight into distances.